Hello there, welcome to Cool Talk and the history of the world. I'm going to do something a little bit different. We started with video 1 with prehistory. We were going in order, but then the civilizations and their histories began to overlap. It could be confusing, so I want to start a timeline. But before I do, we're going to go way back to our beginnings to the Big Bang. And how did we get to the widely accepted theory of our beginnings with the Big Bang? Let's go back in time to early science. Astronomy began in 4000 BCE in Europe and the Middle East. The reason was that as man began to gather less and farm more, he started to observe the skies. Why? Well, it was beneficial to look at the consistency of the annual and seasonal patterns, knowing when to farm and when to prepare for floods. And this here is the Nebra sky disk. It's the oldest known sky object. It's 3,600 years old. It was dug up in central Germany. The ancient thinkers began to study substances and came up with what they call the four main elements: water, earth, air, and fire. And even the idea of the atom came from those days, individual particles at their smallest part. And the ancient thinkers knew that the earth was not flat. So let's get rid of the idea that Columbus proved that the earth was round. That is not true. The ancient thinkers knew the earth was shaped like a sphere. Now, Aristotle was the first to provide evidence for that. What he did was he started measuring the shadows, but he also looked at the stars. And he noticed that in the northern part, he would see certain stars, and in the southern part, he would see other stars. And what does that prove? That the Earth's shape was on a curve. And get this, in 240 BCE, that is over 2,000 years ago, Eratosthenes observed the sun's rays in the city of Syene and Alexandria of Egypt, and he estimated the Earth's circumference at 25,000 miles, and he was only off by 100 miles. Not bad. Now, Aristotle said that the Earth was the center of the universe and that everything rotated around it. He was wrong, but this idea prevailed for 14 centuries. Many scientists proposed that was not true, that the Earth was the one that was rotating, and they would point out things like at certain times of the year that Mars would shine brighter. But scientists would try to make the data fit the model, which is not the way it's supposed to be done. Then finally, in 1545, Nicholas Copernicus from Poland claimed that it was the Earth that rotated and that this accounted for the daily motions of the stars, the moons, and the sun. Kepler would later on expand on this, and Isaac Newton would also expand on these claims with the laws of motions and the forces of gravity. But the church forced him to recant his theories in 1633. Bummer. Lucky for us that around this time came the telescope. Newton was one of the ones that advanced this, but telescopes became larger, they became bigger, and along came micrometers and parabolic mirrors and spectroscopes, more accuracy. We could identify star clusters by 1721 and galaxies. By 1814, we could determine the chemical makeup of the stars. By 1839, we could take photographs for permanent observations and recordings. By 1920, the Hooker telescope discovered galaxies outside of our own and that the universe was expanding. By 1937, we had parabolic dishes, maps of radio emissions. Radiation was detected in the background. All of this supporting the Big Bang theory. And for these advances, we have to thank Galileo and Kepler and Newton, Gascoigne, Huygens, Halley, Messier, Hubble, and other giants and countless unsung heroes. One of them in 1967 was Jocelyn Bell. She discovered the first pulsar. By 1990, the Hubble Space Telescope peered deep into space and time and improved the measurement of the universe's age. By 1993, the Keck Telescope used adaptive optics that adjusted for atmospheric turbulence. And hopefully, by 2021, the James Webb Telescope will be launched. It will succeed the Hubble telescope to provide improved resolution and even more distinct events and objects, the formation of the first galaxies. During all of this, there were advances in the study of atoms as well. John Dalton, in early 1800s, believed that atoms were indivisible, but in the 20th century, Ernest Rutherford said atoms had a substructure, and Albert Einstein stated that matter and energy had an equivalence. In 1912, Henrietta Leavitt claimed that there were links between cycles in light, and she determined light-year distances. In 1919, Edwin Hubble arrived in California. At the time, the view was that the entire universe was in the Milky Way, but Hubble said that the Andromeda Nebula was too far away to be in our galaxy. He also developed Hubble law, which is that the further a distant galaxy is, the greater is the recessional velocity. And with all of these advances in astronomy came advances in cosmology. And to reenact the Big Bang, the CERN collider was created. But even the collider needed the advances in mathematics to see how matter behaves, plus studies in both macroscopic and microscopic properties, and the famous theory of relativity by Albert Einstein, and the union of this relativity and quantum mechanics. Thank you, Stephen Hawking. There are four forces at work in the Big Bang: gravity, electromagnetic force, strong force, and weak interaction. But before we talk about the Big Bang, let's illustrate this. Imagine a swimming pool. If there was no wind, no interceding forces, the water would be perfectly still. Toss a pebble into the center, and the water would disperse outwards in ripples. If the pool was limitless and without interrupting forces, the ripples would go on forever. If you are hovering above, you could observe these ripples, calculate the speeds, and count backwards to beginning of the process, and you will know the exact time that the pebble hit the water. That, in essence, is how we study the Big Bang, but it's not that simple. Imagine that while the ripples move out, that elements in the water form and somewhat disrupt the process, and later that some elements or objects grow hot and then cool and then unite, and then with gravitational forces pull on these objects and make our studies very complicated. Some objects grow dense, so dense that the gravity pulls on objects in the swimming pool and slows down time and space. Then some objects in the swimming pool explode. So these ripples are now hard to read. But because the pool is so large, it takes a long time for the light reflecting on these events to reach us. If we calculate the different observations, we can state when these events happen and when the original event happened. But to complicate matters is the measurement of time. Now, when the pebble hits the water in the swimming pool, you might be content to measure this instant in microseconds. What happens when the pebble hits the water, when it sinks into the water, when it touches the surface, when it's a quarter of the way in the water. And to measure all of this, to be precise, we measure time in the tenths of a second, a hundredth of a second, maybe even a millionth of a second. And you'll probably be content with that. But with the study of the Big Bang, scientists want to know what happened at that very instant. Well, the CERN collider has helped immensely to reenact the event. But we have a problem, and this is the Planck era. What is the Planck era? Well, when the Big Bang, the reenactment of the Big Bang began, it was a span of time, and that time is measured in the trillionth of a trillionth of a trillionth of a second. What happened in that little time frame, we don't know. What happened after the Planck era, that trillionth of a trillionth of a trillionth of a second, can be studied. But what happened before then, we don't know, and we possibly never will. So let's begin. The Big Bang. Boom! The universe is born 13.8 billion years ago. First comes that Planck era. We don't know what happened. And then we don't know what's going on. But beginning with the Planck era, four forces unify. As I mentioned, gravity, electromagnetic force, strong force, and weak interaction. Now the gravity splits off. Inflation begins, lots of mass energy comes into existence, and strong force splits off. And photons dominate this baby universe. Photons are particles representing a quantum of light or other electromagnetic radiation. Now wait a minute, you might be wondering what caused the Big Bang? And if there was nothing, how did the universe begin from nothing? I can't explain it, but I will refer you to the Physics Arxin blog for a better explanation in quantum fluctuations and quantum mechanics, and how the Heisenberg uncertainty principle explains how a vacuum, nothing in other words, will either disappear or expand rapidly, causing a Big Bang. Now, creationists might say that something cannot come from nothing, thereby proving that there was a creator who created the universe. A scientist will counter, fine, but what created the creator, and what did the creator use to create this? What did he use? Did he use nothing? Did he use photons? And where did the photons come from? These questions can go on forever, but you know what? Maybe one day we'll be able to study the Planck era, that trillionth of a trillionth of a trillionth of a second, and see what was going on the instant the Big Bang occurred. But in the meantime, let's move on. Okay, so we have the Big Bang, then we have the Planck era, and then we had photons. Then we had mass particles and antiparticles, such as quarks. They form energy. After that, a weak interaction splits off from the electromagnetic force, and so begins the laws of physics, becoming what they still are today. Then the first protons and neutrons collide. And now we must talk quickly about dark matter. Scientists believe there is a non-luminous material that exists in space in the form of moving or interacting particles, and that within the first second of the Big Bang, helium, hydrogen, and dark matter formed, and there was no light yet. But when the universe was 3 minutes old, the first nuclei is formed. Not an atom, but the center of the atoms, made up of helium and lithium. And that's it for 380,000 years. They go by when the electrons combine with protons to form the first atoms, hydrogen atoms. And what about the photons we mentioned before? Well, they go off to travel into space as radiation. It's a busy universe. The stars that are born form elements and dark matter. There were halos from the spinning of the stars, and supernovas would occasionally erupt, and more elements are born. And then came planets and moons. Now, when our sun was born, which is roughly about 4.6 billion years ago, the gravitational pull swept up the elements around it. Light elements were blown into space as gas, became heavier, and some became rocks and planets. Our Earth was born about 4.5 billion years ago. Originally, it had no atmosphere, no oceans, and was constantly battered by objects. These collisions caused constant heat. Then the crust began to move, magma erupted, and, well, today 30% of the Earth is made up of land, continents. In 1645, a bishop named James Ussher said that the Earth was created on October 23rd, 4004 BCE, and this was accepted by many. However, in the late 18th century, James Hutton said that the Hadrian Wall in Rome was about 1,000 years old, but the rocks there had barely eroded. So the rocks that had eroded had to be much, much older. In 1903, Marie Curie discovers radioactivity, and later radiometric dating is developed. Now, some meteorites that landed on the Earth were believed to be older than the Earth itself. Zircon crystals that were found in Western Australia, the size of dust mites. Now, zircon survives erosion and is an excellent record keeper of the Earth's history. So the Earth is born 4.5 billion years ago, and a mere 100 million years later we had oceans. Microorganisms form, then bacteria and archaea in the ocean. Now, archaea forms nucleus of complex cells. By 3.18 billion years ago, bacteria approached the land. The soil grew rich in organic matter. Then photosynthetic organisms begin to fill our air with oxygen. The oxygen floods the Earth, and complex cells are formed. These complex cells then split to form the foundation for two groups, plants and animals. The oldest fossil that we have to date is seaweed, about 1.2 billion years ago. About 934 million years ago, we had plants. Then came sponges. Then about 650 million years ago, the supercontinents rift and perhaps triggered the Cambrian explosion. By 635 million years ago, a known animal embryo, a relative of the jellyfish, was formed. Then we have arthropods and evidence of fish. Later came insects, spore-like plants, fossils, trees, vertebrates. Vertebrates begin to invade the land, reptile fossils. Then reptiles that became mammal-like. But by 250 million years ago, we had what we call today the Great Dying. 70% of the known animals and plant species die. Now, microbes were the first to photosynthesize, and they first consumed food without light from the deep ocean. Now, bacteria joined bigger cells to form later on plants and animals. And these plants and animals would follow food elsewhere to capture the sunlight. When the earth was flooded with oxygen, many of the first organisms died. They died in shock. But others managed to store the oxygen, and in 1 billion years, virtually all life on Earth was breathing oxygen. Other species got oxygen through membranes or their skin. Now today there are 8 million genetic possible combinations in the human sperm or the human egg. And with sexual behavior, lots of DNA began to be shuffled around. Cells began to build bodies. Single-cell organisms developed into living things with trillions of cells. For example, slime mold began as a single cell, but with stress, it began to band together with other single cells to form multicellular bodies. And these multicellular bodies in other species had different functions. For example, leaves began to develop. They became solar paneled. Male and females developed ways to attract each other. Otherwise, the species would die. And as animals moved or crawled or swam, they developed a battery of sense organs and developed brain stems and nervous systems, and then a full brain itself. And with this came decision making. Now, bigger brains means more complex behavior. Now, you can marvel when you look at a spider creating a spider web to catch insects. So spiders have some intelligence. However, the spider lacks artistic creativity. It will never create a flower-shaped web, for example. It will never do any of that for its own personal amusement. Now, cartilage begins to develop to protect the brain, which is critical for land animals. Then came the vertebrates and skulls. Now, vertebrate animals were fish, the first ones, and they used to suck mud from the bottom of the ocean floor. But when the first fish began to develop jaws, they could eat other things. Vegetation grew in the water, algae. These would stick to seaweed, but some plants needed sunlight, and some of them reached land but clung to the rocks and with time developed roots. Erosion forms the first soil about 3 billion years ago, and bacteria is formed to become particles. And the first land animal to breathe was a pneumodesmus. It looked like a millipede. Some animals developed wings. Arthropods, for example, insects, oldest birds and the oldest bats. Now, the old plants carried sperm, but sperm had to swim to get to the egg on water droplets. But once the plants produced seeds, the sperm became redundant. Now, eggs, for its own protection, began to develop harder shells. Once this could happen, eggs could be laid on land. Amphibians became reptiles. And how do we know all of this? We're still studying, but mostly from fossils. And fossils tell us that 99% of all species that ever lived are now extinct. Living things that died 300 million years ago and squeezed out water and air was pressurized and became coal. Besides coal, we have insects and lizards trapped in amber and dust. Dust? Yes. Dust travels across the oceans, and some of it was trapped in the ice in Greenland and Antarctica. If you take out hard ice cores from frozen land, you can find with specialized equipment dark rings in the ice. These dark rings are dust, millions of years old, trapped in the ice. The ocean tells us a lot too. But did you know that we know more about deep space than we know about the deep ocean? The ocean deep waters create so much pressure that we can't easily go down there to study. So we have to rely mostly on sonar. Studying geology tells us of mass extinctions. 445 million years ago, sea levels fall and destroy many marine invertebrates. 365 million years ago, oxygen levels in the ocean drop, killing many fish and coral reef. 250 million years ago, volcanic eruptions and greenhouse gases caused mass extinction called the Great Dying. 200 million years ago, there was a breakup. The Pangaea breakup increases the volcanic activity, warms the climate, and more species become extinct, but the dinosaurs would dominate. However, about 65 to 66 million years ago, an asteroid struck the Earth, bringing acid rain and dark skies, killing off the dinosaur. And after the dinosaur, plants and animals interact, coexist. For example, plants give insects nectar, and insects provide pollination. They form a partnership. Today, 250,000 species of flowering plants exist, and there are 1 million species of insect. And I mentioned that amphibians developed into reptiles. When they dried out, mammals descended from the reptiles, developing milk for the young, and grasslands appear. Primates became more and more intelligent, flexible, with more dexterity. Modern primates were the orangutan, then the gorilla, the chimpanzee, the bonobo, and then the human. Now, no one can ascertain why for certain that brains grew in the primates, but some state it was because of diet. Others add social interaction. Early prehistoric primates demanded to have quick thinking and decision making. Primates began to walk upright, and the entry point of the spinal cord to the skull was now on the underside, not in the back like today's apes. Neanderthals and Homo sapiens appeared. At larger skulls, Neanderthals had less chin, bulkier eyebrows, short, round chests. And about 200,000 years ago, in Africa, appeared the first humans. And in our next video, we will examine the timeline of the first few thousands of years of human progress, not in one place or one continent, but across the globe at the same time. But for now, tell me what you think. Subscribe or comment below. This is Cool Talk.